Hi, in this video series we'll be talking about Chapter 6, Transcendental Functions. So we'll be defining many functions like the logarithm, the exponential, the power functions, the inverse functions of the circular functions, and the hyperbolic functions and their inverses as well. So we start first by recalling the definition of an inverse function and the differentiation of the inverse function. As you already know, if you have f being a mapping, we say that f has an inverse function if f forms a bijection from its domain into the image set or the range set, which is from I into f of I. Which means, as you already know, that if f is strictly increasing or strictly increasing on its domain or a part of its domain, then on this part f has an inverse function denoted f minus 1 that goes from the range of f into the domain or this part of the domain of f. So if f goes from I into R, then f minus 1, the inverse function, would be going from f of I, which is the range, into I. And for all x in I, f minus 1 of f of x. So if you take x in the domain of f, you calculate the image of of x, and then you calculate the image by f minus 1, which will bring it back to the domain of f. We will have x. And for all y in the range of f, so y is an image of some x, then f minus 1 of y will bring it back to the domain of f, and then f of what we obtained will bring us back to to y. So f minus 1 is exactly the inverse function of f because it's calculating the pre-images of y. And moreover, the graphs of f and f minus 1 are symmetric with respect to the straight line y equal x. So to sum it up and to add the differentiability, we'll say that if we have f going from I into R, a differentiable and strictly monotonic function on I, then f has an inverse function which is also differentiable and strictly monotonic. And if f is increasing, then f minus 1 is increasing as well, and if f is decreasing, then f minus 1 is decreasing as well. And f minus 1 of f of x is equal to f of f minus 1 of x equals to x. So finally, f minus 1 of f of something or f of f minus 1 of something will be the identity, will be the mapping that for x it corresponds x. And the derivative of f minus 1 at a point f of x, so at a point in the range of f, it's equal to 1 over the derivative of f at the point x, which is the pre-image of what's in here. So to prove this, first, if f is strictly monotonic, then it's injective, of course, because you cannot have two numbers in the domain of f having the same image. Then if we take f from this part of its domain or its domain I into the range f of I, then any point in the range has a pre-image. Therefore, f is surjective as well. So f is bijective. Since f is bijective, then it has an inverse function, f minus 1. Of course, it's bijective from I into f of I. And since we constructed the inverse function as so it will be differentiable if f is differentiable. We can prove it using the definition of the derivative, but it's also visible by construction. So by construction of f, it will have the graph symmetric of the graph of f with respect to y equal x. So f minus 1 will be, there is no reason that to have a point where f minus 1 is not differentiable. So f minus 1, we take it as differentiable. And then the composition of f minus 1 and f is differentiable on I, which means that for all x in I, f prime of x, if f prime of x is different than 0, then the derivative of f minus 1 prime of fx is 1 over f prime of x, because in fact if you differentiate f minus 1 of f of x prime, calculate the derivative of this prime, using the theorem of differentiation for composite functions, it will give you an f prime of x times f minus 1 prime of x, if you want. And this, since this function is the identity, so it's the function that for all x it corresponds x, then its derivative is equal to 1. So taking this term down in here, we'll have the theorem result. Let's look at this example. Use the inverse function theorem to calculate the derivative of the inverse function of f of x equal 2 over x minus 1, and compare the obtained result with the derivative obtained by differentiating the function directly. So first we take the function f of x equal 2 over x minus 1, and we calculate the inverse function. You know how to do it maybe, but if you don't know, all you have to do is to write y equal 2 over x minus 1, and then calculate x function of y. So it means that x minus 1 times y is equal to 2, then x is equal to 2 plus y, yes, over y. Okay, and then you replace x by y and y by x, which will give y equal x plus 2 over x. Then the function f minus 1 of x, it needs x in here, is equal to x plus 2 over x. And this way we calculate the inverse function f minus 1, the expression of f minus 1. Now, if we want to calculate the derivative of f minus 1 directly, we'll calculate the derivative of this function, which is u prime v minus v prime u over v squared, and it will give us minus 2 over x squared. And on another hand, if we want to calculate the derivative using of f minus 1, of course, using the last theorem, we will say that f minus 1 prime at a point x, of course, the theorem says that f minus 1 prime at f of x is equal to 1 over f prime of x, right? So the x is in here, replaces the f of x in here. The idea is that we should read this theorem as follows. We should say that the derivative of f minus 1 at a given point is equal to 1 over the derivative of f at the pre-image of this point. You see? So you should not be confused about f of x and x. Here we have something that is in the domain of f minus 1, which is in the range of f. And what you should have in here is the pre-image of what's in here. Okay, so if here we have x, because we want to calculate the derivative of f minus 1 at a point x, any point x in the domain of f minus 1, so it will be 1 over the derivative of f at the pre-image of this point, which is f minus 1 of x. So it's equal to 1 over the derivative of f is the derivative of 2 over x minus 1, which is equal to minus 2 over x minus 1 squared. So this is what we should take at f prime in here, and we should replace x by f minus 1 of x, so it will be minus 2 over f minus 1 of x minus 1 to the power 2, which is equal to f minus 1 of x. I know it, it's x plus 2 over x. I replace, I do the calculation, and I will obtain the same result that I obtained directly in here. So this is how I should use the theorem. Let's take another example. Use the inverse function theorem to calculate the derivative of the inverse function of f of x equal 1 over x plus 2 at a point 1. So what we need to calculate is f minus 1 prime at the point 1, which is equal to 1 over f prime at the pre-image of 1, f minus 1 of 1. So it's 1 over f minus 1 of, f prime of minus 1, because minus 1 is the pre-image of 1, and to know this, we calculate f of x equals to 1. It means that 1 over x plus 2 equals to 1, then x equals to minus 1. So the point whose image is 1 is minus 1. So it's f minus 1 of 1, which is minus 1. 1 over f prime of minus 1, we replace minus 1 in the derivative of f, and it will give us -1. So this is how we use the theorem. We define now the first function in the chapter, which is the natural logarithm. So the natural logarithm is the function defined as being the primitive of the function 1 over x such that its value at 1 is equal to 0. So it's the primitive of 1 over x that vanishes at 0, because as you know, if we have a primitive of a function, or if we have a function and we calculate the primitive is not unique, because if you change a constant, if you add a constant to this primitive, it will stay a primitive to the function. So we take the primitive that vanishes at 0 and we call it the natural logarithm. And of course the primitive of 1 over x exists because 1 over x is a continuous function. So ln will be the function defined from 0 plus infinity into r, because we say it's the primitive of 1 over x on the part 0 plus infinity. And then it's equal to the integral of 1 over t between 1 and x. So since ln of x is the primitive of 1 over t, or of 1 over x, then it's ln of x minus ln of 1, and since we take it the function that vanished at 1, so ln of 1 is equal to 0, then this integral will be equal to ln of x. So let's study a little bit this function. First, this function is differentiable, of course, because it's defined as being the primitive of 1 over x. So it's differentiable and its derivative is 1 over x. Okay, so this is the first formula that you should know, that the derivative of ln of x is 1 over x, of course, when x belongs to 0 plus infinity deprived of 0. It's an open interval. So this proves that ln is strictly increasing and that it's a c infinity function, because its first derivative, it's 1 over x, and 1 over x is a c infinity function. So it's a c infinity function on r plus star, and moreover, since ln of 1 is equal to 0, so we have a function that is increasing, and at 1 the value is equal to 0, then before 1 it was negative and after 1 it's positive. So that's why ln of x is negative when x is between 0 and 1, and it's positive when x is between 1 and plus infinity. Be careful that in here we don't count on what you know already about the logarithm. What I'm trying to do in here is to take this definition as a starting point and then try to prove all the properties that you know about the logarithm, starting from this definition and the properties that I will be proving. Okay, so first, using what I know from this definition, I was able to know the derivative of the logarithm, and then that it's negative between 0 and 1 and positive between 1 and plus infinity. But let me check something with you. What if I calculate the derivative of ln of lambda x? So if you take, for example, ln of lambda x, and you want to calculate the derivative, okay, forget what you know from last year. ln of lambda x is a composite function. It's ln of f of x, let's say, with f of x is equal to lambda x. Then its derivative will be the derivative of ln times u prime, so times f prime of x, which will be 1 over lambda x, the derivative of ln, times the derivative of what's inside, which is lambda. So it's using the differentiation of the composite function. So it will be 1 over x. And that's why if the derivative of ln of lambda x is equal to 1 over x, then the derivative of ln of lambda x is the same as the derivative of ln of x. Then ln of lambda x and ln of x are the same, but there might be a constant that differentiates them. So it should be, it's equal to ln of x plus some given constant c, right? So if we want to calculate c, we can take a particular value of x. Let's, for example, x equals to 1. Then ln of lambda is equal to 0 plus c. Then c is equal to ln of lambda. Therefore, ln of lambda x is equal to ln of x plus ln of lambda. And this is how you have the formula that you already heard of course. It's ln of ab equals to ln of a plus ln of b. Okay, this is how we prove it. That's why, going back to the properties of Ln, we can prove that for all AB in R plus star, Ln of AB is equal to Ln of A plus Ln of B. If we take now Ln of A, it should be equal to Ln of A over B times B, right? It's the same thing. Then it's equal, using this first property, to Ln of A over B plus Ln of B, right? That's why Ln of A over B is equal to Ln of A minus Ln of B. So this is how we prove this second property. So again, until now, I started with the definition, and everything I'm proving it using the initial definition of the logarithm. So this is how we prove these two properties. Of course, we can extend now what we already proved to a given number of points. So instead of having A and B, we can have A1, A2, A3, A4 until AN, and we prove that the Ln of the product of AI is equal to the sum of the Ln of AIs, and which can also be used to prove this. So in fact, this first property in here we can prove it by induction, and the second property can be proved using the first property for all the A's being the same. Now let's suppose that we want to know what is happening when x tends to plus infinity. Ln of x is going where? So if x tends to plus infinity, let's try to see what happens if we consider that Ln of x is going to a given limit L. So suppose that the limit of Ln of x when x tends to plus infinity is a finite limit L. What happens next? In fact, this means that Ln of 2x when x tends to plus infinity, or the limit when x tends to plus infinity, is also equal to L, because we have in here something that is going to plus infinity, and Ln plus infinity will be equal to L, right? But since we know that Ln of 2x is equal to Ln of 2 plus Ln of x, it means that the limit of Ln of 2x when x tends to plus infinity is equal to the limit when x tends to plus infinity of Ln of 2 plus Ln of x, which is equal to Ln of 2 plus L. And so we have two limits for the function Ln of 2x. The first one is L, and the second one is L plus Ln of 2. But since the limit is unique, so this is impossible, so we have a contradiction. Therefore, we cannot have a finite limit for Ln of x when x tends to plus infinity, and that's why when x tends to plus infinity, Ln of x, since it's increasing, it will go, of course, for plus infinity. Now, what will happen to Ln of x when x tends to 0 plus? So we want to calculate the limit when x tends to 0 plus, of course, because the function is defined on 0 plus infinity, of Ln of x. So it will be equal to the limit of Ln of 1 over big X as big X tends to plus infinity, right? Which is equal to the limit as big X tends to plus infinity of Ln of 1 minus Ln of x. So Ln of 1 is equal to 0, so it will be equal to minus infinity. Therefore, when x tends to 0 plus, Ln of x will go to minus infinity. And this is given in the following theorem. Okay, so when Ln of x, or when x tends to plus infinity, Ln of x tends to plus infinity, and when x tends to 0 plus, Ln of x tends to minus infinity. Now we can draw the table of variations of f, being Ln of x, so it's an increasing function from minus infinity to plus infinity as x goes from 0 to plus infinity, and the derivative, of course, is positive. That's why the function is increasing. And we know that we have a vertical asymptote x equals 0 in the neighborhood of minus infinity, in the neighborhood of 4y, of course. But what about when x tends to plus infinity? Do we have an asymptote, or do we have an asymptotic direction? So let's check it. We know that 1 over t is less than 1 over square root of t when t belongs to 1 to plus infinity, right? So we integrate both sides in here. We will have the integral of 1 of t between 1 and x, which is ln of x, and the integral of 1 over square root of t between 1 and x, which is 2 radical x minus 2. And this is always positive because we have t that is between 1 and plus infinity, and x greater than 1. So if we divide everybody by x, we'll have ln of x over x between 0 and this term in here. So if we take the limit of this term when x tends to plus infinity, it's equal to 0. So ln of x over x tends to 0. And so the limit of f of x over x tends to 0 means that we have a horizontal asymptotic direction, so an asymptotic direction parallel to the x-axis. So we can now draw the function ln of x. So it has a vertical asymptote in here, it has an asymptotic direction in here parallel to the x-axis, and we can also see that the straight line y equal x is going like this. So when x becomes big, the image of x on ln is much less than the image of x on the straight line y equal x, which also interprets the result that we obtained, that limit of ln of x over x is equal to 0 when x tends to plus infinity, which means that x is much greater than ln of x when x tends to plus infinity. And this is a formula, of course, that you should know. You can also calculate the tangent, the equation of the tangent at the point 1 in here, and it will be y equal x minus 1. So it has a slope parallel to the slope of y equal x. We define now the second function, which is the exponential function. In fact, since ln is a function that goes from 0 infinity to minus infinity plus infinity, and it's differentiable, strictly monotonic on 0 plus infinity, then it defines a bijection. Then it has an inverse function that will be denoted exponential or exp. It goes from the range of ln, so it's minus infinity plus infinity, into the domain of ln, which is 0 plus infinity, and it's differentiable and strictly monotonic as ln. And we have, of course, exponential of ln of x, which is f minus 1 of f of x equals to x, and the ln of exponential of x equals to x. Of course, here x should be in 0 plus infinity because it's in the domain of ln, and in here x can be in R because it's the domain of exp of x. And we can calculate the derivative as well using the theorem of the derivative of the inverse function, which will lead us to saying that the derivative of exponential of x is 1 over the derivative of ln at the point pre-image of x, which is exponential x. So it will be equal, since the derivative of ln is 1 over x, then it's equal to 1 over exponential x, 1 over exponential x. So it's 1 over exponential x, which is exponential x. So this is how we define the function exponential, and we can prove the following properties that are all based on the properties obtained for ln. They can be proven using everything we proved for ln. So first, exponential 0. So it's the number whose image by ln is 0, so it's 1. Then for all ab, exponential a plus b is equal to exponential a times exponential b. In fact, this is due to the fact that if you take ln of exponential a exponential b, it's equal to ln of exponential a plus ln of exponential b. Which is equal to ln of exponential a is a plus ln of exponential b is b. And on another side, if you calculate ln of exponential a plus b, of course it's equal to a plus b. So it's the same thing. That's why exponential a exponential b is equal to exponential a plus b. So this is how you prove why you have this formula in here, which is the most important formula for exponential now. Then, of course, you can deduce from all this that exponential minus a is 1 over exponential a, and using the limits obtained for ln using the symmetry with respect to y equal x, we can prove that exponential x tends to plus infinity when x tends to plus infinity, and exponential x tends to 0 when x tends to minus infinity. And also we can prove that exponential x minus 1 over x goes to 1 as x tends to 0. So now we can draw the table of variations of exponential x. F prime is positive, so the function is increasing. And we have the limits, which means that here we have a horizontal asymptote, y equals to 0. And using the symmetry with ln, here we should have an asymptotic direction parallel to the y-axis. And also because of the symmetry, we can say that for any x, exponential x is positive, and for any x between 0 and plus infinity, exponential x is greater than 1. In fact, due to the formula that we obtained in here, which is very similar to the formula we have for the powers. So you know that you have, like, if you have x to the power a plus b is equal to x to the power a times x to the power b, right? Since we have this kind of relation for exponential, which is similar to the power representation, then the exponential function will be denoted as ex, because it will be treated as if it was a power, because it has the same property as the power. So the curve of the function ex now is symmetric to the curve of ln of x, and we will draw it in here. You see, if this function is ln, you have in green the exponential x in here, which is always positive because of the symmetry, and at 0, the value of ex is equal to 1. So to finish with the logarithm and the exponential, we will define the logarithm of base a, which will be equal to the log of x base a is equal to ln of x over ln of a. Of course, this should not be equals to 0, ln of a, so a should be between 0 and 1 or 1 plus infinity. So a cannot be equal to 1. And the function log base a of x will be defined on r plus star, because x should be between 0 and plus infinity, so that this ln or ln of x can be defined. In this case, the logarithm base e, which is the number that is the image of 1 with the function exponential, so the logarithm base e of x is equal to ln of x. In fact, if you take the function ln of x, take the number whose image is 1, it will be this number e. And this number e will be the number, of course, that is the image of 1 by the function exponential. So e1 is equal to e. Okay, so this number will satisfy ln of e is equal to 1. So if you take this number in here, and if you take this number, the e, and as being the base for this function, you will have ln of x over ln of e, which is equal to 1, then it's ln of x. And we have the following properties for the logarithm base a. So log base a of 1 for whatever a is equal always to 0, because ln of 1 is equal to 0. And also we have this property, which is similar to the one for ln, because it's deduced from ln in here. And also for all a between 0, 1 and 1 plus infinity, for all b between 0, 1, 1 plus infinity, log base p of x equal log base p of a times log base a of x. It's easy to prove also. And for all a between 0 and 1, 1 plus infinity, log base 1 over a of x being equal to ln of x over ln of 1 over a, which is minus ln of a, so it's equal to minus log base a of x. Now, if you calculate the derivative of the logarithm base a, it will be equal to the derivative of ln of x over ln of a, which is 1 over x ln a. So it means that x is positive, of course, but a can be between 0 and 1, which means that ln of a can be negative, or it can be greater than 1, which means that ln of a is positive. So it can be positive if a is greater than 1, and negative if a is less than 1. So if a is greater than 1, we have this table of variations where the function ln or log x base a is increasing, and if a is negative, or sorry, less than 1, we have this table of variations where the function logarithm of x base a is decreasing, which means that if this function is ln of x, then if you take the logarithm base, let's say 10, it will be something doing like this. So this is the logarithm base 10 of x, for example. And if you take the base as being less than e, it will be something like this. So this is the logarithm base, let's say 2 of x. But if you take the base being between 0 and 1, then you will have something like this. So this is, let's say, for example, the logarithm base 0.5 of x.